go ahead and start recording. There we go. Who's here? I hope everyone's here. I turned just double check that I remember to do that. Yeah, the waiting room is turned off. So you all should be able to enter just fine. We have been working lately on section 3.2, which is about the derivative as a function. Okay, not just as like a particular individual thing, like not just like a number, like it's like a slope of a tangent line, but rather as a function in its own right. Okay, so let's review. We had recently the example f of x equals x squared, and we found that the derivative of that is 2x. Okay, so x squared looks like this. It's got 1, -1, like that. Let me see if I can actually graph that a little cleaner. Say 1 is here, and then 1 would be like there on the y-axis. -1, 1. So we have these points, right? 1, 1, 1, -1, 1, and then like 2, 4, right? 2, 4, -2, 4, those points up there, right? So that is our x squared graph. The graph of 2x is a little different than that. The graph of 2x, what it does is it shows you for each x value, it outputs the like slope of the tangent line from the original graph. So for example, on the original graph, when x equals 0, there's this like bottom, like the parabola has its vertex at that point. And what do you think the slope of the tangent line is at that point right there, where it like bottoms out, the minimum point?
Zero.
That's right. It's 0. Yeah. There's I kind of want to bring back the here. I want to bring back this guy. Let's get rid of the parts we don't need here. Secant lines. And a plus h. Let's just grab the tangent line. Yeah, as you can see, a tangent line sort of hits like horizontal, right? Whenever the point reaches a maximum or a minimum, there are these 0 slope lines, which are horizontal lines. Yeah. So so that's what's happening right here. Boop, 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 boop. And so that means that we would graph the derivative at 0, 0, like this. Let's put some scale on here. Okay. So now graphing the derivative, if I move on to another point, like let's say look at this point 1, 1 that's on the original graph, what I would do is I would imagine the tangent line at that point right there, and then I would guess at what the slope is. And it's a little hard to see what this slope is. Let me see if I can draw it exactly right. There we go. That's about right. So so that's the slope right here. And if you look carefully at what's happening, when x goes over 1, draw that like this. When x goes over by 1 unit, y actually goes up by 2 units. Oops, sorry, I don't know what I did. I must have pressed something I didn't mean to press. You can see it again over here. There's a point on that line down here. If we go backwards by 1 unit, we go down by 2 units. Okay, so over 1 up 2 is our slope there, all right? So, so that means that when x equals 1 on the graph of the derivative, what we're going to plot is height 2, like this, okay? And then over here, if we move on one more step, x equals 2, we would look at the graph of this derivative. We would look at the graph of this tangent line right here and try to figure out what its slope is. And let me just see if I can do that properly. A little bit of a challenge, but it should be about like that. Okay, it's really close. It should pass through this point right down here. Okay, I've got a very rough graph, which is why it's not, not ideal. But that down there, that tangent line there, it should end up with a slope of 4. Okay, you can see the -1, -4 right there. Slope of 4 on that one. So when x equals 2, y equals 4. And the point is that all of the y values on this graph correspond to the slopes of the tangent lines on the original graph. And I've just done it at 3 points, 0, 1, and 2, but we could have done it at any point in between, okay? So just to demonstrate that, right? I did it at 0, here's x squared. I did it at 0, 1, and 2, but we could have also done it in between, right? So here's all the points in between 0 and 1, they have gradually increasing slopes, right? And then between 1 and 2, still gradually increasing slopes. So those slopes are we got all the possible slope values in between. And if I actually tell Desmos to graph f prime of x, like using the apostrophe right here as the prime symbol, it will do it. Desmos understands derivatives. It can graph a derivative right here. So just use the apostrophe, f prime, and there it graphs it. And then what we can do is we can see the point, instead of just plotting the point a, f of a, we can also plot the point a, f prime of a, and we can see that point on the derivative as well. So here it is at 0. Then when we get to 1, there at x equals 1, we have this slope of 2, and we have a point right here on the graph of the derivative at height 2. When we get to x equals 2, now we have a derivative. Well, now we have a tangent line with a slope of 4. And on the graph of the derivative, the point on the derivative has a height of 4, and so on. Okay. So that's this connection between the two graphs. All right, this goes on like this. And you can imagine it going backwards as well. If you move to the left at -1, we have this negatively sloping line, tangent line, which is going to give us a negative output on the derivative graph, and so on, getting more and more negative as you go off this direction. So there we go. And if you look at what we have,
I have a question.
We've got x squared is a parabola and 2x is a straight line of slope 2, and that's exactly what we're seeing. Okay, go ahead, Adam.
Do we have to print out exercise set 3?
Oh, great question. Okay, not about what we're doing right now, but about the assignment. Yes, you're gonna have to print it out. I failed to get that out to you guys in time. I should have printed it for you yesterday, and I just didn't think about that. And I didn't do it. So yeah, I'll show you where to find it, everybody. And I'll give you this reminder that exercise set 3 is due tomorrow night. Okay. Oh, hey. Graydon has also put out an announcement about the updated SI session. We'll look at that in a second. Okay, so on the week 4 announcement, I put due this week, exercise set 3 due Wednesday, February 1 at 11:59 p.m. That's tomorrow night. submit it here. So the actual exercise set itself you can obtain from this link. It's in the content area as well, but this link takes you directly to the file. So here is the file. It has 3 pages this time. Okay, in part because I needed space for all these graphs. I wouldn't say it's actually longer. I just gave you more space. So the first 2 pages of exercise set 3 is what we've been working on. Here is a function, and we're evaluating the derivative at a point using evaluating a limit version, the limit definition of the derivative, so the limit of the difference quotient. So that's what this page is for. And then we're finding the equation of a tangent line. Okay, taught you guys how to do that. And then we're going to generalize that, like I showed you in class yesterday. And we're going to find f prime of x as a function, and then use that function to evaluate f prime of 4 and f prime of 3. And then answer a quick question about what that tells you about the shape of the graph. So then the second page, or the third page rather, is all about graphing. So here I've I'll have to draw a couple of graphs. I'll explain this in a minute. This is recognizing like which one of these is the function and which one of them is the derivative. It's kind of a fun exercise. So one of these is the function f, and one of them is the derivative f prime, and you have to identify which is which. And then this is another fun thing to do where you look at the graph and you try to draw the derivative. Okay, so without any algebra, without any like numbers or functions explicitly defined, you just look at the graph and attempt to draw the derivative of it. It's all based on slopes. So, yeah, that's due tomorrow night, and you guys can print that out on your own, please. Okay. Thanks for that reminder, Adam. All right.
I have a question.
Oh, go ahead, Rowan.
Instead of looking at the parabola and basically doing like the up 2 over 1, why can't you just plug in the numbers into 2x?
Oh, you can. But the point is that you get the same graph both ways. So, we could have graphed this by just plugging numbers into 2x and obtained this graph of slope 2. Yes, and we would have got this exact graph. But I was trying to make help you guys make the connection that it's not just because you happened to get 2x from the derivative process that this is that graph. This graph also has a connection to the original graph, which, in terms of outputs being the same as the slope values. Does that make sense?
Yeah, thank you.
Yeah, good. Okay, so let's look at something a little more challenging. Let's try it now without oh man, what am I saying? Let's try it without the actual like functions defined. Okay. So I'm going to show you guys a thing. And then I'll show you where you can practice it.
Another question.
Go ahead.
How do you find the OpenStax textbook?
It's a link. We have a link on the D2L page. I'll show you that too. Right here. See all this information widget? It's here all the time. It never goes away. It's after the Zoom room, it's the very first link. OpenStax. It's a link that says textbook. It's very aptly named. And then you navigate the textbook through here. So table of contents, chapter 1, chapter 2, chapter 3. So we're in chapter 3 now. So so you want to do homework for chapter 3, 3.1. And it's down here. Here it is. Okie doke. Okay, so let's say we have this graph. This is the graph of a function. Let's call this y equals f of x. Our goal is going to be to graph the derivative of this function. Let's do it in red. So how can we even go about starting to graph the derivative of this function? Well, the first thing we could do is look for points on the graph where we reach a maximum or a minimum. So like this point, for example. That point right there. At that x value, we have a horizontal tangent line. So that means that the derivative at that x value, which I'm estimating to be a little less than -4 here, the derivative at that point right there is going to have a value of 0. Right? And then you can find more of those. There's one over here, horizontal. Here we go. So at that x value, the derivative will cross the x-axis like that. Right? And over here, there's another one right about there, horizontal. So it's going to cross the x-axis. Okay. So there we go. So we have 3 points graphed on our derivative graph, right? That's a great way to get started. Is looking for those horizontal tangent points. And that tells us where to put our x-intercepts on the derivative graph. That make sense? Because of this connection between the derivative points, their y-coordinates are equal to the slopes on the original graph, right? So now I need to figure out how to go in between. So how is it going to go? Is it going to go like sort of like, you know, that or something? Or maybe the opposite of that? Maybe it's going to go like this. Or maybe it's going to do something else. Maybe it's going to do like touch there and then go this way and go up and then maybe go touch like that. Like, how exactly is this going to go, right? Is it going to be all positive, but then just dips down and hits the hits those points or something? Like, how do we fill it in between? Here's how you figure it out. You guys remember the difference between positive slopes and negative slopes? If you go from left to right, like positive slope goes up and negative slope goes down. Okay, in general, the direction of the graph is going to be the direction of the slopes. And so you can pay attention to where it's going to go like this. You can see that the slope values here are all going to be negative, right? So on this interval of the graph, in this x interval between these 2 points, the derivative graph is going to be somewhere down here. Right? It's going to be negative because of the fact that all these slopes are negative. Does that make sense? Now, exactly how negative and like, well, we'll figure that out in a minute. So far, let's just say, all right, so we want our derivative graph to be somewhere in this vicinity down here. So what I'm actually going to do is I'm going to sort of like cross out, maybe let's use like a gray to sort of gray out what's up here and say that up there is now like off limits. Okay, I'm not going to use that area. So it's got to be down here somewhere or like that somehow. Similarly, on this next interval over here, we are seeing slopes that are like positive, right? The slopes here are all positive slopes. They're generally going up, right? Because the graph is going up. So that means that our derivative should be up here the entire time. Somehow it's going to connect this point to this point by going up. And so we will gray out what's down below. This region is then grayed out. Okay. And we can do that for every interval between x-intercepts. So like over here, you can see it's going to be heading more down over here in that tiny interval on the end. So I'm going to sort of gray out what's over here. Right? Let's make that a little less intrusive. There we go. And finally, it's positive over here. So I'm going to gray out the negative area. So now we roughly know we're going to be in this part, and then this part, and then this part, and then this part. So that's how we're going to go. So now the next question is like, just how far down does it go, right? Like how far down and where along that interval is it going to reach the sort of maximum point? Is it going to be here, or is it going to be here, or is it going to be here? Like that's the only two questions we need to figure out. And we only need to do this very roughly. It doesn't have to be like perfect. I'm just going to show you a strategy for guessing. So if we look back at our original graph here, which I'm going to sort of embolden to make it stand out a little better for you. What we want to do is look along the segment of the graph we're working with and look for what we think is the steepest point on that graph. Okay, so for example, on this interval right here, I would guess that the steepest point on this graph is going to occur right about there. Would you agree with me? Right? It's going to be right about there. It's not over here because this is more shallow. Like it's not as steep, right? And this is not as steep either. But the steepest point is going to be somewhere right in the middle where it gets really steep. It's like if this was a hill and you were like climbing the hill, it would be relatively easy, then it would get harder, and then it would get easy again. Right? So you look for that steepest point. And then what we want to do is just estimate real roughly like what approximately is going to be the slope of a tangent line right there. If we imagine drawing that tangent line, what approximately is that slope going to be? I'm going to guess that that's pretty close to -1, maybe a little bit steeper than -1. What do you guys think? It's almost like down 1 unit over 1 unit, but it's a little more than that. It's a little, you have to go, if you go over 1, I think you go down. That distance looks to me like a little more than 1 unit distance on this grid system. Do you see how I'm guessing here? It's very rough. So, so I'm going to sort of erase my tangent line that I drew there. Oopsies. Well, I guess we can keep it, and do sort of like a that there is estimating. And so I'm gonna put that down here. Like -1 is here. -1 is here. So I'm going to make it a little lower than -1, like about there. There's my rough estimate for where the minimum should occur. Now I know that I can complete my graph by coming down to that point and then coming back up again. Okay, so these are all negative values, but we have a little bit negative for the shallow slopes here. We have a little more negative, the most negative at that steepest point. And then we have, again, back up to just a little bit negative for the shallow negative slopes on the other end. Yeah, all this is being recorded. Yep, folks. Someone asked, but we are recording. Yep. Okay, so I can do the same thing over here and guess my point. About maybe like there approximately is maybe where I get the steepest point, and that tangent line is going to be about 1, again maybe a little more than 1. So I'm going to guess roughly there, and then it's going to go negative, and it's kind of hard to tell exactly how negative it gets, but something like that. And then over here it's going to be negative, and at the end it's going to get to a slope of about that, which is roughly a 1/1 kind of slope. So I'm going to go to about there. And there it is. There's my guess at what the tangent line is. Y equals f prime of x. Not tangent line, sorry, that's the wrong word. The derivative graph is the right word to use there. So where did I get this graph from? You guys can do this exercise. There's a website that I'll send you called Calculus Applets Using GeoGebra. This is a website that was built quite a long time ago by a guy named Mark Renault from Shippensburg University. Mark's a super nice guy. I've chatted with him once or twice on the internet, and told him I'm very grateful for his website because I've been using this website for years. It has a lot of cool stuff. I don't think I've shown you guys anything in here yet, but I don't use it as quite as often as I used to because I've switched over to using more GeoGebra. But a few of these are still really good. So number 10 here is the one that we've been working. If you click on number 10, it'll take you to this page. And what it will do is it will give you, let me see, I kind of, yeah, there we go. It will give you a graph, and it'll give you this thing that you can grab and move around. So this is supposed to sort of be a, this is supposed to be the graph of the derivative. This is like this thing here that you can move. This is supposed to be the derivative graph. And you can just kind of place it, like kind of get it to like, just kind of manipulate it until it looks just about like you want it to. So I'm going to try to make this look like I had it on the other page. So I'm going to try to mimic the blue graph from this side over here. So -2 is approximately where we hit our minimum there. So it looks sort of like this. And then -4, by the time we got to -4, we were just above, right? So sort of like that. And then maybe about like that. So there's a very rough picture. I'm trying to make that follow the blue graph. And then I can say, check accuracy. And it says I'm 91% accurate. And I can show results. And then it shows me the correct graph of the derivative. And I can see how close I got. So this is a way that you can practice. And then you can reset, 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 reset. And practice the same exercise over and over and over again as many times as you want. With different curves. They're always going to be smooth curves, never any like points or corners. But it's a good way to practice like figuring out what the graph of the derivative looks like. Check your accuracy and then show the result to see if you're right. Okay, so I'll send you guys a link to this website if you want to look at it right now. I'll just put it in the chat for you. There it is. There it is.
Do you mind putting it on the D12 page?
Yep, I'll put it on D12 as well. I'll do that after.
Right. Thank you.
Sure thing. Yeah. The other one you might want to try is identify the derivative function number 12. This one is kind of cool. This is similar again to one of the exercises I put on the worksheet where I gave you these pictures that have like two graphs. You got to identify which one is the function, which one is the derivative of the function. This is a little bit similar to that. The idea is to identify which of the possibilities is the correct graph of the derivative of the function shown. So here we have the blue graph. That is the function. You can think of that as f. And then we're trying to identify which of these three graphs is the graph of f prime. Only one of them is correct. And we can kind of figure it out based on a few details. So like, for example, we can see that this blue graph should have like horizontal tangent lines right over here about -3.5, just over here at like -0.5, maybe just to the left of the axis. And then another one over here about at 4. So we should be looking for x-intercepts. So like this has an x-intercept at somewhere around -3. Looks like it's not quite in the right place. It should have another x-intercept right here at the x value -0.5, but this one does not. So I can rule this one out. If I click on it, you can see it says no, I was wrong. This one up here looks pretty close. It's got an x value at x-intercept at -3.5, one at -0.5, and another one close to 4. So that's a possibility. And this one, I can rule this out as well because it's missing that x-intercept there. So in this case, I can narrow it down to get the right answer here just by looking at where the x-intercepts should be. Okay, but sometimes you get one where it's like there's two graphs that have nearly the right thing, nearly the right shape, but it's just a matter of where, like, you have to look at the positives and the negatives. Like, it should be positive here, or it should be negative here, that kind of thing. Let me see if I can find a good one. Yeah, it's kind of hard to tell. Oh, this one's kind of good. So like in this one here, this green graph and this red graph, they both have an x-intercept at about -2.5 or -3. That's approximately where this peak is over here. So that peak where you'd have a horizontal tangent corresponds to this x-intercept and this x-intercept, right? But you can see that the green graph is positive to the left of that, whereas the red graph is negative to the left of that. And the original function, if we look to the left of that point where there should be a horizontal tangent line, the graph on this portion to the left of -3, this graph is going up, right? The slopes of the tangent lines on this portion of the graph would be positive. So the derivative graph should be positive. It should be above the x-axis. The green one is above the x-axis. So this is a possibility, but the red one is below the x-axis. So that rules out the red one. You can see it's not correct. The green one, I believe, is correct because if we compare these two, which are sort of similar in shape, the brown one has another x-intercept down over here on the end. It goes from negative and it hits the x-axis and goes to positive. This means that the original function would have had to go from it would have had to have another horizontal tangent line. It would go from going down with a negative slope to going up with a positive slope. But as we can see on this original graph, it just goes down, 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 and it never actually comes back up again. It never has another horizontal tangent line. So that can't possibly be correct. It can't have an x-intercept there. And we see, yes, indeed, it's no. So that means it's got to be this one. The graph just continues to be negative here without ever hitting the x-axis again, because this graph just keeps going down. So I don't know. This is doing a bunch of these over and over again can be good practice because it just helps you develop these skills of understanding the relationships between the graphs. And so please look at that. Again, these were numbers 10 and 12 in Mark's giant list of cool calculus applets. Okay. Okay. So that's a little bit about graphing. Let's get back to well, let's do one more graph and then that'll segue us into the next topic here. So what if I have a graph that looks something like this? And this is my function y equals f of x. Okay. If there's a straight line right here, then at any point on this graph, the tangent line is just going to coincide with that straight line. So at any point here, my tangent line is the exact same line as the straight line that the point is on. That's the way it works for straight lines, right? The tangent line is coinciding with the line. And so to figure out what the derivative graph should look like, we just need to know the slope of this line. Let's say this slope is about, let's see, it looks like we go up one. Let's find another point that's on here. This looks to be about there and there. So let's say this point is the point like 4, 3, and this point is the point 0, 0. If we can find 2 points that are on that line, then we can know the slope. What's the slope? Up 3/4? 3/4, right? And then over here, I'm going to get a similar situation where the slopes are all negative, and here it goes down 3/3. So this slope over here is about -1. So when I draw the graph, I have to do for this segment here, for these x values where the graph is going up like this, I have to draw my graph at a constant value of 3/4. So 3/4 is about right here. And so I'm just going to draw, I'm just going to draw a straight line at 3/4, at horizontal 3/4, just like that. Because the slope is constant, and so the derivative is constant, which means horizontal line. That's what a constant graph looks like. And then down here, I need the slope at -1. So wherever -1 is on my axis, as soon as it goes over this point, then it becomes -1. And it goes like this. So now the question becomes, what the heck happens here? Okay, what happens here? Well, what is the slope of the tangent line at this point? What do we think that is? Zero is not a bad guess because of the fact that whenever we had a maximum or minimum before, it was 0. The difference is that these maximums and minimums are smooth.
I remember we learned that there's no tangent line for a point like that.
That's correct. Yes, we talked about this very, very early on, right? When we first started talking about tangents at the beginning of the semester. So tangent slope is undefined. And the reason for that is at this point, the limit of the difference quotient, which I'll write out here, the limit of that difference quotient does not exist. Okay, the reason is because if you try to take the limit as delta x approaches 0 from the left, you would get that slope. Let me do it in like bright pink or something. You get that slope from the left side. But then if you took the limit as delta x approaches 0 from the right side, you would get that slope. And those two slopes aren't equal to each other. So like in terms of the limit, it would be like, it would actually be exactly this. It would actually be this jump right here. The limit doesn't exist because there's a jump, right? So it simply doesn't exist. And so at both of these endpoints right here, where the graph is approaching 4, we put an open circle. Because neither of those endpoints is actually going to have a closed filled in dot, because the derivative graph should not exist. It shouldn't have an output at all when x equals 4. The tangent slope is undefined. So this is an example of a point where the function is not differentiable. That's a word I got to introduce. Not differentiable. Okay, vocabulary time. To find a derivative, that action, like the process or just the act of doing it, to find a derivative is to, quote, differentiate a function. Okay, so this is a verb. Differentiate is a verb. It's to do a derivative, to find a derivative, sometimes you hear the phrase to take a derivative. To take a derivative. This is common phrasing. So you'll hear me say this a lot. If we need to take a function and get its derivative for some purpose, I'll say, let's differentiate this function. Okay. So this is something you guys have already been doing. If the derivative exists, oops. A function f is called differentiable, which is differentiatable. It's possible to differentiate. Otherwise, it's not differentiable or sometimes non-differentiable. Sort of wild words. Non-differentiable. Okay. So that's what we just did up here. It's an example of a point on a graph where it's non-differentiable. There's a few different ways that you can have a non-differentiable point. One is a sharp point like this. Non-differentiable can occur for one of several reasons. It can occur because of a sharp corner or point. This type of thing is called a cusp or a corner, depending on exactly how it's shaped. You don't need to, it's not super important to know the difference between a cusp and a corner. I just want you to know that when there's a sharp point like that, that's non-differentiable. Another way you can get non-differentiable is because of any discontinuity, like a jump, a hole, or a vertical asymptote, or of some kind. So this would be anytime f is not continuous, or discontinuous would be the word we used, I guess. Discontinuous. It is also non-differentiable. Okay. So here's a fact that sort of is related to this. In order for f of x, a function, to be differentiable, it must be continuous. I guess first is a bit silly. There's no order to this, but it must be continuous. But continuity does not guarantee, there we go, differentiability. F of x must also be what's called smooth. Okay. And smooth just means it's a nice curve. It doesn't have a sharp point or a corner. That's smooth. So smooth, the differentiable is like a very, these terms are all actually very like rigorously defined. Like the word smooth in mathematics has a very specific meaning. We're not really going to get into that. Like, it's a little bit beyond the scope of this class. But if you take more math classes, you might eventually start, getting into a class where you use the term smooth very, very like precisely. It's a little more than just saying the derivative exists. It's slightly more complex than that. But basically for this class, I mean, I'm using the word smooth in a very intuitive way to mean like it's a smooth curve. It doesn't have a sharp corner. It's smooth. It doesn't have any like jumps or jagged edges or anything like that. Sometimes there can be functions that don't look smooth, but actually are if you zoom in on them enough. So just as an example to finish the day, let's look at something like x to the power 127. X to the power 127, if you look at the graph here, it looks like a dog's leg in a road or something. It looks like a corner, right? It looks like it turns two sharp corners. But these are not actually sharp corners. These are actually smooth corners. And the way you can tell is if you zoom in sufficiently, you can see that it looks smooth. Okay. And this function is differentiable. This is a function that is going to have a defined derivative. I can graph f prime if I set it equal to f, I graph f prime of x. Yep, that graph exists. It exists everywhere actually for all x values. It's a little hard to tell, but it does. And I can make this as big as I want. I can make this 1027. Doesn't matter how big it is. It's still technically going to be a nice smooth corner down here. I can throw some more zeros on here and see how sharp I can make it look. Oh, it looks really sharp, but if I zoom in enough, it's still a nice smooth corner, right? So looks can sometimes be deceiving. However, to contrast that with an actual sharp corner, if I look at a function like x to the power 2/3, x to the power 2/3 has what's called a cusp at this point right here. If I zoom in on this point, it is a genuine sharp corner, and this is not going to ever look smooth no matter how far I zoom in. Same with like the absolute value of x, for example. That looks like a corner, and if I zoom in on it, it still looks like a corner. There's no way I'm ever going to zoom in far enough to make it look like a smooth curve. Those are examples of actual points where the function is not differentiable. So just a word of warning: don't leap to conclusions too quickly when dealing with corners. Okay, I think that's it for the day, folks. Everybody have a lovely afternoon, and I will see you again on campus tomorrow. Thank you.